Today we're going to talk about dividing radicals. And then one of the main things we're going to talk about is this property where if I have two radicals with the same index divided, I can write them as one big radical. Or vice versa, if I have one large radical, I can split that large radical into one radical divided by another radical. So with this, it helps me simplify radicals where I have a root in the denominator. So if I look at number 1, if I want to simplify this radical, I could split it as root 3 over root 16, which would simplify into root 3 over 4. And now this would be fully simplified. When dealing with radicals, we want to make sure that our denominator doesn't have a radical. We always want our denominator to be free of radicals and fully reduced. So when looking at number 2, I need to remove the radical from the denominator. So there's two ways I could go about this. The first way I could go about it, I'm actually going to do the way that we did in example 1. Instead of having two little radicals, I'm going to change this to be one large radical. And once I have one large radical, I can simplify. So if I have 18 over 2, that's 9. And if I have x5 over x3, that's x2. Well, the square root of 9x squared would just be 3x. The other way I could simplify this is by trying to make the denominator a perfect square. And we'll talk about this a little bit more below, but I'll give you an example here. So if I have the square root of 18x to the 5th over the square root of 2x to the 3rd, I want to multiply the top and the bottom by some square root that'll make my denominator a perfect square, such as what we saw here, this 9x squared. That was a perfect square. So if I look at my denominator, well, I know this is an index of 2. So I know I need pairs. So 2 times 2 will give me 4, which is a perfect square. And I want an even index, so let's say I multiply by another x. Now, what that'll give me in the bottom is the square root of 4x to the 4th, which would give me 2x squared. Now I can see that my radical is gone from my denominator, so I have fully simplified that denominator so far. But whatever I multiply on the bottom, I must multiply by the same thing on the top. So when I multiply by 2x on the top, I'm going to get 36x to the 6th, which the square root of that would be 6x to the 3rd, which when I reduce that, I'll get 3x, which was the same as what I saw above. Now, whichever method you choose, I would like you to simplify example 3. I would recommend doing the first method by making a large radical. Pause the video now. When you are ready, play the video. All right, let's see how you did. So I took the two small roots and made it one large root. I then did 162 divided by 3, which was 54. Then I broke down the 54, and I broke down the y cubed. So y cubed is 3y's, which means I'd have one group of 3, so 1y comes out. When I broke down the 54, I got 3 3's, so 1 3 comes out and the 2 stays in. So my final answer is 3y cubed root of 2. All right, so now we're going to do some more simplifying. So let's look at these points at the top here. So my first point says in order for a radical to be fully simplified, there needs to be no perfect square factors under the radical. So that means I still shouldn't have square root of 9, square root of 25, anything like that. I also should make sure all of my radicals are fully simplified. Next, to talk about that there should be no radicals in the denominator. Okay, so I should have no radicals in the bottom of my fractions. And there should be, now this last one says no denominators under radicals. That's a little confusing. That means that I shouldn't have a large radical with a fraction still inside. as well as this second one means I shouldn't have any type of radical in the denominator at all. So both of those are not allowed. So we're going to work on something called rationalizing the denominator. So a radical is an irrational number, and we want to make sure that our denominator always has a rational number. So if I look at 4, I need to somehow rationalize this denominator. So what I want to do is I want to multiply by some radical that will make the denominator a perfect square, because now it's a square root. Well, the smallest perfect square I can think of is 4. So that means if I multiply by root 2, my denominator will become a root 4, and the square root of 4 is 2. So that's exactly what I want. I want to multiply by something that will give me a perfect square that will then become a non-root number. But whatever I multiply the bottom, I must multiply by the top. So if I multiply by root 2, I'm going to get 3 root 10. 3 root 10. I always want to check to see if that root can be simplified. Well, 10 breaks down into 5 and 2, so that radical cannot be simplified. So therefore, my final answer would be 3 root 10 over 2. Now, let's say this outside number, instead of a 3, what if it was a 4 or a 6? Then I'd want to divide it with my denominator and simplify that fraction further. But in this case, it's a 3, and that doesn't divide evenly by 2, so I'm going to leave it the way it is. All right, so let's look at 5. So I'm going to start off by splitting 5 into 2 roots. So square root of x over square root of xy, or 8y, excuse me. Now, again, I want to multiply by something that's going to make my denominator a perfect square. Whatever I multiply the bottom by, I must multiply the top by. So I have a few options. So 8 times 8 would give me 64, which is a perfect square. So I could multiply by 8. I could also multiply by 2, because 8 times 2 is 16. 16 is also a perfect square. Either of those options will work. It just depends on how much you want to simplify at the end. Now, y is not a perfect square, but if I get y squared, that's a perfect square. So I'm going to multiply by 2y. And when I do that, in the bottom, I'm going to get the square root of 16y squared. Well, the square root of 16y squared would be 4y. So that's great. I got the radical out of my denominator. On the top, I'm going to have the square root of 2xy. And that will not simplify. So square root of 2xy over 4y will be my final answer for this one. All right, this last one's going to be a little trickier. Or this next one, I mean. Number 6. So this is now, I'm looking for perfect cubes because I have a cube root. So let's talk about perfect cubes. So 1 cubed is 1. 2 cubed is 8. 3 cubed, 3 cubed is 27. 4 cubed is 64. And just for good riddance, 5 cubed is 125. So in order to simplify this denominator, I need to multiply by the cubed root of something that's going to give me a perfect cube. So now I already have a 4, so I need to look at my perfect cubes and say, okay, 4 goes into which ones of these? Well, I could multiply 4 by 2 to give me 8, or I could multiply 4 by 16 to give me 64. But typically, we always want to try to do the smallest number. So I'm going to do 4 times 2, because that will give me an 8 in the bottom, and the cubed root of 8 is 2. Then I have an x squared. Well, I need a group of 3, so I already have 2 x's, so I just need 1 more x. Now I'm going to do this in the top and in the bottom. So when I multiply my bottom, I'm going to get the cubed root of 8x cubed. Well, the cubed root of 8 is 2, and the cubed root of x to the third is x. So that's great. Now my denominator no longer has a radical. When I multiply in the top, I'm going to get the cubed root of 14x squared y squared. Now 14 breaks down into 2 and 7, so I'm not going to get any groups of 2's. So my numerator is actually not going to simplify, so it's just going to stay the cubed root of 14x squared y squared all over 2x. All right, this last one's going to be similar to number 6, but now I have a fourth root, so now I got to think about perfect fourth powers. So 1 to the fourth power is 1. 2 to the fourth power is 16. 3 to the fourth power is 81. I'm going to leave it at that. So I'm going to first start off by splitting this into the fourth root of 3a over the fourth root of 4b squared c. Now, again, I need to multiply my denominator by the fourth root of something that's going to give me a perfect fourth root. So I already have a 4, and if I look at my options, well, 16 is a perfect fourth root. So 4 times 4 will give me 16 in the denominator. Now I have b squared. Well, with a fourth index, I want groups of 4. So that means I need 2 more b's and 3 more c's in order to have those perfect groups that I'm looking for. And then remember, whatever I do to the bottom, I must do to the top. So in the bottom, I'm going to get the fourth root of 16, b to the fourth, c to the fourth. In the numerator, I'm going to get the fourth root of 12ab squared c cubed. So if I look at the bottom and I go to simplify, the fourth root of 16 is 2. The fourth root of b to the fourth is b. The fourth root of c to the fourth is c. In the top, if I go to break down 12, well, 12 is not going to give me any groups of 4. Neither is a or b squared or c to the third. So my numerator is just going to stay 12ab squared c to the third. And so that would be my final answer. So the last thing we're going to talk about is what happens when we don't just have a single radical in the denominator, when we have a binomial in the denominator, such as 2 plus square root of 3. So when we have a binomial in our denominator, well, our denominator is, like I said, 2 plus square root of 3. We want to multiply by something called its conjugate. And this is really important. You're going to use this word throughout your math career. Well, the conjugate is the same binomial. I'm just going to change whatever symbol is in between the numbers. So in this case, my conjugate is 2 minus root 3 because my original problem was addition. If my original problem was subtraction, my conjugate would be addition. So how this works is if I multiply by the conjugate, what's going to happen is my radicals are going to subtract in my denominator. I'll show you what I mean in example 8. So I have 5 minus root 2. So I want to multiply by the conjugate, which is 5 plus root 2. And I want to do that on the top and the bottom, because whatever I do to the bottom, I must do to the top. Now, I'm going to multiply out the bottom first. And again, I'm going to have to FOIL. So 5 times 5 is 25. 5 times root 2 is positive 5 root 2. Negative root 2 times 5 is negative 5 root 2. And negative root 2 plus root 2 is negative root 4. Now, I'm going to FOIL out the top. So 3 times 5 is 15. 3 times root 2 is 3 root 2. So my denominator's actually, or sorry, my numerator is going to stay the same for right now. My denominator, I'm going to work on simplifying. So first, the reason I multiply by the conjugate and the reason I changed the sign from minus to plus was so that way these middle terms will subtract. If I have positive 5 root 2 and negative 5 root 2, those are going to subtract, so those will become 0. Now I just have 25 minus root 4. Well, root 4 is 2. So I really just have 25 minus 2, which means my denominator will be 23. And this would be my final answer. So the conjugate allows us to simplify the denominator and remove the radical because our middle terms end up subtracting. So, using this conjugate idea, I would like you to try 9, 10, and 11. Remember, you're always changing the sign. If it's subtraction, the conjugate will be addition. If it's addition, the conjugate will be subtraction. When you are done with 9, 10, and 11, or after each one, play the video and see if you got them right. So if we look at number 9, the conjugate would be root 3 plus 1. I'm going to multiply that on the top and the bottom. So when I distribute on the top, I get root 9 plus root 3. On the bottom, I get root 9 plus root 3 minus root 3 minus 1. Now again, that plus 3 and that minus 3, they're going to subtract. And then I have some perfect squares here. Well, each of my square root of 9s, those become 3s. So my final answer is I'm going to get 3 plus root 3 all over 2. In number 10, my conjugate would be root 3 plus 5, which I'd multiply on the top and the bottom. In the top, I would distribute, and I would get 2 root 21 plus 2 root 35. In the bottom, I would get root 9 plus root 15 minus root 15 minus root 25. Again, when I'm looking at these, I have a positive root 5 and a positive root 15 and a negative root 15. So those are going to subtract. Square root of 9 is 3, and my square root of negative 25 is negative 5. So I end up with a negative 2 in the denominator. Now, this is one more step that we need to talk about simplifying. So I have a 2 in front of my root 21, and I have a 2 in front of my root 35. Those are both divisible by negative 2. So I did 2 divided by negative 2 and 2 divided by negative 2. And that left me with negative root 21 minus root 35. So keep in mind, kind of like when we did quadratics, if all 3 of those values can be simplified, we've got to make sure that we're doing that. All right, number 11, our conjugate is 3 minus root 6. So I multiply that by the bottom and by the top. When I distribute in the top, I get 12x minus 4x root 6. In the bottom, when I distribute, I get 9 minus 3 root 6 plus 3 root 6 minus root 36. Again, those middle numbers are going to subtract. Square root of 36 is 6, so I get 9 minus 6 in the denominator, which will give me 3. And so my final answer would be 12x minus 4x root 6 over 3. Technically, my numerator is factorable, so you could also factor it and leave it as like this. Either way would be fine with me. My main reason for factoring would be if this 4 in front and this 3 in the bottom could be divided and simplified. In this case, it can't. But my main reason for factoring would have been in order to simplify that.